Okay. Hi, everybody. Good morning. A very good morning to all. Right. How many of you are there? 1, 2, 3, 4, 5, 6. Only
Morning,
six
sir.
of you. Good morning. Good morning. Right. So yeah, I see only 6 of you. Right. Maybe wait for 2, 3 more minutes for your friends to join, and then we'll start. Right. So someone was asking me a question. I think it was Hansini who asked me. I think.
Yes.
What kind of problems will be numericals will be asked in
Structure
atomic
of atom chapter.
structure of atom. Basically, from Bohr's model, right? We have radius formula. Rn is equal to 0.0529 n by z, right? And then that is one thing. Radius, velocity, mvr is equal to nh by 2 pi, right? And then from that energy, E is equal to kz squared minus kz squared, right? And then transition energy, more importantly, emission spectrum of hydrogen. That is Lyman series, Balmer series. That one definitely one problem will come. Other things I don't know, but definitely problems will come from Lyman series, Balmer series kind of questions. That Rydberg's constant, all these things will come, right? And de Broglie's wavelength. Lambda is equal to h by mv or h by p, right? And then you can get questions from quantum numbers. Definitely you will get quantum numbers question. Okay, you know how the quantum numbers works, right? So that you will get, and obviously you will get questions from Heisenberg's uncertainty principle, right? So wherever you wrote equations, right, wherever we have blocked some equations, right, and all those kind of questions can come. And I say very I can predict for sure these kind of questions will be from quantum numbers and will be from emission spectrum of hydrogen. That is your what is that, Lyman series, Balmer series kind of questions will definitely come. Other than that, yes, radius, Bohr's all the equations, de Broglie's, and your Heisenberg's uncertainty principle, right? So these are the questions which can be asked. Okay, Hamsini.
Okay, sir. Thank you.
Right? Yeah. Okay. Right. So now we have how many? 8 of you. A good enough number, I guess. We can start. Right. Okay. Let me share my screen, people. Oh, someone said that they have to leave by something, right? Can I leave by 12 because I have function to attend? Yeah, sure. Sure, Shailaja, you can leave 12:30. No problem.
Thank you, sir.
Right. 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 So you guys are 11th and today is 12th September. Right. Okay. So last class, actually, I have to go to the previous thing only, right? That's better because I was filling tables. Where was it? Yesterday's thing. Yeah, I think this one, right? Okay, right. So what did we complete is until 6, we saw AB6. Okay, steric number 6, we taught till AB6 and SF6 or SCL6 was the example. And we even saw when I have dissimilar species, how am I going to put it? Right, I think we saw, right? SF4. Oops. One second, guys. Right. So yeah, SF4Cl2, you have all you have to remember is that the dissimilar atom should be placed in the opposite corners of the octahedron. Right. So this is how you write. Right. Either Cl opposite or Cl opposite. This is how we write. Okay. Now it can be dissimilar atoms or even lone pairs. If you have 2 lone pairs, for example, right? So obviously they must be placed in the opposite corners of the octahedron. If you have only 1 lone pair, then there is no question here. Please do not confuse in octahedral complexes, octahedral compounds, that is steric number 6 with AB6. right? There is no question of axial and equatorial bonds. Do not confuse yourself. The axial and equatorial bonds exist only and only for your trigonal bipiramidal geometry. That is steric number 5. Okay, right, fine. Moving on to see the next type in steric number 6 itself. I have to grab certain things. Wait. Okay, so steric number still steric number 6 only, right? But I'm going to say AB5L. That is 5 bonding atoms and 1 lone pair. Okay, now it's very simple, people, to understand the geometry. Geometry is still going to be octahedral. So if I have to draw it, so I'm talking about AB5L. So I know the geometry is octahedral, or it is also called as what? Octahedral is also called as? Guys, what is octahedral also called as?
Square bipyramidal.
Right. It's a very easy to understand. I have a square, one at the top, one at the bottom. Square bipyramidal, but we generally use only octahedral complex. Right. Anyways, so now I have 5 bonding atoms. Right. Say now 5 bonding atoms. Right. I can put lone pair anywhere, but just for your understanding, right, I put the lone pair here. Okay. Right. Now this is my geometry. Geometry is still octahedral. Right. Now, when I go to the shape, again, I have to forget that this is not there. Right. I should not be including this. Okay. Now, if that happens, I will have something like this. So basically, I have a square, and on top of the square, I have one pyramid. Okay. Now, this was square bipyramidal, the geometry. Right now, this is going to be square pyramidal, only one pyramid. There in the bottom, there is nothing. Right here, I don't have anything. Right. So now you put the lone pair in the shape, you just remove the lone pair, and what you see is that I have a square and one pyramid at the top. So it is going to become square pyramidal. Okay. Right. Now we have to take some examples. Right. Say if I have to take some examples, AB5L, let me take maybe IF5 kind of molecule, or say CLF5, right? CLF5 will work. Yeah, CLF5 will work. Right. Now how CLF5 will work? 7 valence electrons, right? 5 bonding atoms, obviously. So 5 fluorine will go, 5 electrons will go. So what is remaining is 2 electrons. So it becomes one lone pair. Okay, so CLF5, BRF5, something like that. All these interhalogen compounds. These are what are called as interhalogen compounds. Basically, 2 halogens combined together to form these kind of compounds. You'll study more about them when you go to 12th class. Okay, so for now, you can remember their shapes. Right now, for them, the geometry is octahedral. Right, it belongs. I hope you understand. It belongs to category AB5L. 5 bonding atoms and 1 lone pair. I just found out. Right. And their shape would have been square pyramidal shape. Okay, right. So let us fill these things here. Right. So AB5L, it is still octahedral. The geometry is still octahedral, but the shape has become square pyramidal shape. Again, bond angle, we don't have to speak. An example is going to be CLF5. That's a good example we can take. Okay, right. So that is about AB5L, right? Next category, still in steric number 6, I can go for AB4L2. Okay, I can go for AB4L2, right? Now AB4L2, we'll see again what happens. So when I go to AB4L2, right? Say again, the geometry is same, right? But you have to follow the rule. The rule is that you have 2 lone pairs here. The 2 lone pairs must be placed in the opposite corners of the octahedron, either here and here, or here and here, or here and here. Either way, right? You have to make sure that they are placed in the opposite corners of the octahedron, just to make sure that there is lesser repulsion. Right? Now again, what you do, you remove this you remove this, again, the shape is still octahedral, right? You remove the two lone pairs, and if you write it, right, all I have is just a square. Is it not? Because the two lone pairs are gone, right? Now, obviously, what I understand is this shape is what is going to be called as square planar. Basically, I have a square in the same plane. Is it not? Right? Because the one at the top and the bottom are gone because they are lone pairs. The only thing remaining is in this plane itself, I have 4 bonding atoms, and that's why it's going to be called as square planar. Okay, can you give me an example, B? Can you give me an example, guys, for AB4L2 type of molecules? One example. One example, can you give me for AB4L2?
XCF4.
Yes, absolutely. Right. Now
ICl4 minus.
ICl4 minus is also good. Right. Anyways, I will check both of them. Right. So XC is having 8 valence electrons. Right. 4 of them are gone with fluorine. So 4 is remaining. Obviously, 2 lone pairs. So 4 bonding atoms, 2 lone pairs. AB4L2. Right. Same way in ICl4 minus, we'll see what happens. Right. Now it should be 4 and it should be ICl4 minus, but minus sign should go to chlorine. Yeah, okay, right, understood. So okay, can you do me a favor? Can you draw the Lewis dot structure for ICl4 minus? Draw the Lewis dot structure for ICl4 minus, and then we can conclude whether it is going to form AB4L2 or not. First of all, ICl4 minus, does it even exist? ICl4 negative charge goes to iodine, then it makes sense. But if it doesn't go, okay, fine, let me check. Right, say now iodine is there, 7 valence electrons, right?
Yeah,
Definitely
it goes to the iodine. Negative charge goes to
if
iodine.
it goes to iodine, it works. Yes, I know. Right, if iodine has negative charge on iodine, then it will work, but it is not the case. Whenever you have negative charge, it has to go to bonding atoms. But we'll try to understand whether it happens or not. Okay, right. So now it has 7 valence electrons. 1, 2, 3, 4, 5, 6. Okay, right. 1 second, guys. Hold on. Just hold on. Yeah, now it's fine. So yes, we will just try this out. So iodine has 7 valence electrons, but should I write it like this? Fine, okay, we'll try what happens. Okay, fine. Say chlorine, say basically 3 Cls and 1 Cl minus is what I understand. Okay, so we'll try to do this. Okay, say now 1 Cl minus we can keep here, right? Cl minus is going to have 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right, and other 3 are going to be 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Again 1. Okay, 1, 2, 3, 4, 5, 6, 7. Another chlorine is there. Let me. So I have Cl 1, 2, 3, 4, 5, 6, 7. So now this chlorine will take this one, this chlorine will take this one, and this chlorine will take only 1 electron, guys. Okay, this electron is still remaining. Okay, and this I can tell that this is going to form a coordinate bond. Okay, this is going to form a coordinate bond because this is already filled. Okay, obviously, iodine will take all the electrons which are shared here. Obviously, along with these two electrons. But this electron is not shared with this, right? What I understand is there is 1, 2, only 3 electrons are coming. So yeah, for this particular case, people
Sir,
will
actually, you have to draw another electrons with.
1, 2,
Sir, in the
3,
central
4.
atom.
Absolutely, absolutely. Yes. So now I just remove this particular electron. Yes, correct. Then it works. My bad. Right? One more lone pair is there on iodine. Right? So now, yes, it works. Right? So now you have 1, 2, 3, 4, 5, 6, 7 electrons on iodine. Okay. Now this is gone. This is gone. This is gone. And these 2 electrons are going to come out as coordinate bond. So now check how many lone pairs are there. This is one lone pair. This is the second lone pair. Okay, right? So definitely there's going to be a coordinate bond. So if I write it properly, I have Cl, 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 and a coordinate bond with Cl minus. Obviously, there are 2 lone pairs on iodine. Okay, so definitely it belongs to AB4L2 category because 4 bonding atoms and 2 lone pairs. Okay, right. So now the shape is going to be square planar. It's very much understood, very easy. Right? And the geometry is octahedral. So let us fill these things here. Where is it? Yeah, right. So now we took AB4L2. The shape, the geometry is still octahedral, but the shape has become square planar. Bond angle, we don't have to worry about it. Right? And examples can be XCF4, ICL4 minus, right? All these can be examples. Okay, right. And do you have steric number 7, people, for you? Do you have steric number 7 in your
Okay.
books? No, right? IF7, it's called pentagonal bipyramidal geometry. Did you study anything like that?
Yes, sir.
You studied, right? So last one, right? One more thing, and this is very rare. Okay, I'll just write it here. 7, steric number 7 is very rare. Okay, it is going to form sp3d3 hybridization. Okay, sp3d3 hybridization. Now the shape and geometry, we don't have to go into the details. Say first only we'll take is AB7. There are so many types, but we don't have to go into details. Only AB7 we'll see. Right, now AB7 is going to look like this. Okay, now if I tell you the shape and geometry, then I think you'll be able to better understand. It is going to be called as pentagonal bipyramidal. Okay, obviously the shape and the geometry are same, right? An example for this molecule is IF7. Okay, example for this molecule is IF7. Now, how this pentagonal bipyramidal geometry looks, this is how it will look. Now draw a pentagon first. Okay, draw a pentagon and all the vertex you put bonding atoms at all the corners and then you join. Okay, right? Now pentagon is done, pentagonal bipyramidal is simple. Now I have to put one on the top, one on the bottom. Okay, now if you have to understand what I'm trying to say, assume that say the pentagon goes like this, or say the pentagon goes like this, right? This is in this plane, right? And one towards me, one towards you, bonding atoms. Okay, so that is what is my pentagonal bipyramidal geometry or shape. Right, this alone you have to remember. That's it. Now, okay, people. Right. So now,
Sir?
yeah, tell me.
Sir, are there any other examples of pentagonal bipyramidal?
Yes. If you go to coordination complexes, but you don't know that, I have ruthenium OH 7 times. There are something like this kind of complexes plus. Okay, you don't have to worry about what are these brackets and what are these compounds. Yes, there are other examples, but the only example which you have to remember for 11th is IF7. No other example you have to remember. But there are so many other examples.
Huh?
One of them is, yeah.
Sir, here now you're talking about the shape or the geometry?
In this case, there is no lone pair, right? So geometry and shape are same. Okay.
Sir, I have one example for geometry.
Okay.
ZEF6.
Sorry,
XCF6. XCF6.
Okay. XCF6. Okay. Oh yeah, this also works. Absolutely. Oh, okay. X, okay. This does not come under this, guys. This is a good example. Right, let me tell you what is this. Okay, say since you have asked for it, right, but I don't think that is there in your syllabus. In steric number 7, sp3d3 hybridization, one more example I can have, that is AB6L. Okay,
Yes,
AB6.
sir. That is what I told. Geometry is same, but shape will
Yeah,
differ.
geometry is same. Shape, I'll tell you what is it. Okay, so AB6L, the example I can take is XCF6. You can easily understand how it is. 8 valence electrons, 6 are gone for fluorine, total 2 electrons left out, 1 lone pair. Okay, so 6 bonding atoms and 1 lone pair make it 7 steric number. Right, now the geometry is fine, pentagonal bipyramidal, but the shape is not derived from pentagonal bipyramidal. It is actually derived from octahedral complexes. Okay, so now this geometry or this shape is going to be a little complex shape. This is how it is going to look, right? Say, or if I tell you the shape, it will be better. The shape, I don't have the space here, I'll write it here. The shape is what is called as distorted octahedral. Geometry is fine, pentagonal bipyramidal geometry, right? But the shape of AB6L, that is XCF6 kind of molecule, is distorted octahedral, right? So now what you do is you draw a normal octahedral, right? You write B and B. Now somewhere randomly you put a lone pair. Okay, somewhere randomly you put a lone pair. Basically, it is it should have been an octahedral if this was not there, right? But since this lone pair is there, the octahedral is distorted. It's something like disfigured face, or say I don't know, some disfigured. Say for example, like you must have seen your old vessels in which you drink water. Sombu, we call it in Tamil. Right, so if it's an old thing, you might see some deformations on the sombu, right? That again is nothing but distorted sombu, right? In this case, it is going to be distorted octahedral, right?
Sir?
Not a perfect, yeah.
Sure, then what's the difference between distorted octahedral and pentagonal bipyramidal?
Pentagonal bipyramidal is a proper shape. This is proper shape exists, right? But they are not able to come up with any name for this particular shape. So they just said that, okay, it looks little like octahedral, so we'll call it as distorted octahedral. That's it. This is a proper shape, right? This we can define the shape, but we cannot define this shape. Hope you're able to get the point. Yes.
Okay, sir.
Right. You don't have to worry about this. Just remember that it is going to have distorted octahedral. That's it. Right. That's all is required. And the example is XCF6 for AB6L. Okay. Right. So with this, your VSEPR and valence bond theory is over, right? And I'm telling you people, MCQs, right? MCQs will come, if at all it's going to come from this chapter, majority of questions will come from this particular table which we saw, right? Whatever the table which we filled. Now, what you're going to do is do not mug up anything here. Like obviously, all this should come very spontaneously to you. Right, you know bent rule, you know how trigonal pyramidal becomes seesaw, how trigonal pyramidal becomes T-shaped, right? Or please do not mug it up. If you mug it up, it is going to be very difficult. What you do, they'll give you some compound, right? Now they'll ask you the shape or the geometry. Look at carefully whether they're asking the shape or the geometry in the question. Right, so accordingly, what you have to do, look at the compound and try to fit them in any of these types which you saw, AB5 or AB4L, AB something, AB3, whatever it is. Try to fit them. If you fit that in that particular type, you know what is the shape, what is the geometry, what is the bond angle, everything you know. Okay, this is how questions will be asked, and we have discussed all the examples here. Yeah, other than this, very few examples are remaining for all the categories. Okay, almost all of them we discussed, right? So now again, please do not mark up the examples also, for heaven's sake. Please do not do that, people. That really spoils the essence of learning. Okay, it's all very logical. Whatever we saw, I think now I have taught you in such a way that you do not have to by heart any shape or any geometry for any type of molecule. Okay, so please do follow what we discussed. I don't know how they taught you in school, but I think I tried to give you a better picture, and I think I succeeded. Okay, Fine. So that is about your VSCPR and your, what is that? Valence bond theory. Okay. So now today, what I want to concentrate on is this bond angles. Like I told you yesterday, if I give you two compounds, right? If I give you two compounds, I mean not two compounds, say 3 or 4 compounds, right? Now I'll ask you to arrange them in the order of bond angles. Right now, if lone pair is not there, very simple, right? If no lone pair, then bond angle is very easy. Is it not? For example, if I ask you for BF3 molecule, what is the bond angle? What will you tell me? For BF3 molecule, if I ask you what is the bond angle, what will you tell me? Guys, are you hearing any background noise?
Sir, could you repeat, sir?
Yeah, once again, are you getting any background noise?
No, sir.
No, sir, it's fine.
Fine, right? Okay. So what I was asking is, if BF3 molecule I have, what is the bond angle here?
120.
120, right? Now, please understand, for you to answer these bond angle questions, you must know the geometry and shapes. If not, you will not be able to answer these questions. Okay. For you to arrange certain molecules in the ascending order, descending order of the bond angle, you must know the geometry and the shapes. If not, you'll not be able to answer these questions. Okay. So I know BF3 is going to have trigonal planar geometry, right? This is how the shape will look, or the geometry will look. All the bond angles are 120 degrees. Right. Same way, I ask you, for example, CH4, I ask you what is the bond angle, what will be your answer?
Sir, it's tetrahedral with no lone pair, but forgot the bond length. 90
Very
degree.
simple. 109 degree, 5 minutes.
Yeah, 109.
Okay, so this is very, as he said, it is going to be tetrahedral, no lone pair. Right now, when you don't have lone pair, you have concrete values of bond angle. That's what I'm trying to say. For example, say if I ask you, I have beryllium chloride or say CO2, what is the bond angle here?
It would be lesser than 109.
Beryllium chloride and CO2, what will be the bond angle? It will be lesser than 109. Why? What shape they have? What shape they have? CO2 and beryllium chloride.
Sir, no, sir. It would be the same.
Yeah, both of them will have the same bond angle. I'm asking, what is the shape of both of them?
Tetrahedral.
Do I have 4? I have only 2, right? How is tetrahedral? Steric
Linear,
number is
sir.
what? Steric number is 2 without any lone pair. Obviously, it is linear. So what is the bond angle then?
180.
180 degree.
That is what I told you. If you're not well versed with your shapes and geometries, this particular part will be a hectic, it's nightmare. Okay, so please practice. The moment I ask you, I give you a molecule, ask you what is the geometry and shape, it just should, like in a flash of a second, it should come to your mind. Okay, so this is the geometry, this is the shape. Like that much you have to practice. Right? Okay. So fine. Now, if I ask you, say it's very simple. Like if I ask you a very easy question, I have beryllium chloride, CH4, or let me take, say, okay, fine, CO2. I take SO3, right? And say I take SO4 minus. Okay, and I ask you to arrange them in the order of bond angle. What will be your answer? Arrange them in the order of bond angle, which is going to have maximum bond angle, which is going to have minimum bond angle.
CO2 will be maximum.
Okay, because obviously here the bond angle is 180 degrees, right? Okay, then?
Sir, SO3 is 120.
SO3 is 120, very simple, right? SO3, double bond, double bond, double bond. Oh, no lone pairs on sulfur. So sulfur has 6 valence electrons, 6 electrons are gone. So the shape is obviously trigonal planar. So this is 120. What about SO2 minus?
Sir, octahedral.
For octahedral, how many bonding atoms should be there?
Oh, sorry, sir. No, sir.
Try to find the shape, guys. Everybody, try to find the shape.
Tetrahedral 109.5.
Absolutely, absolutely true, right? It's very simple to understand. Sulfur, this is how it looks, right? Now you see 1, 2, 3, 4, 5, 6. 6 electrons are gone with sulfur, no lone pairs. So it belongs to the category AB4, right? So definitely it's tetrahedral. So it's 109 degree, 5 minutes. So now this would have been the order in which the bond angles are there.
Sir,
Yeah, tell me.
sir, does SO4 exist?
No. SO2 minus only exist. Ion only exists. SO2 exists.
And if we have a charge on any molecule
Hmm.
and the elemental form, will the shape be same for both the cases? For example, if we have iodine and we have
Okay.
iodine plus,
Okay. No,
will the shape
say, see, like say for example, I take IF4 plus and say IF4 minus, and assuming the fact that IF4 exists, but IF4 doesn't
yes,
exist.
sir. Okay.
Right. But definitely you see the shape will be different here, because what happens? Now the positive charge goes to iodine, right? So now I had 7 valence electrons. Now I'll have only 6 valence electrons. So now this will be of the form AB4L. How? Right? 6 valence electrons are there. 4 are gone with fluorine. So 2 electrons are left out, 1 lone pair. Right? Now this belongs to the category AB4L. AB4L, what will be the shape? First of all, AB4 would have been what geometry? Trigonal biparallel geometry.
Yes, sir.
So now
Shape
one of the lone pairs
seesaw.
should go to seesaw. Absolutely. Right. It is seesaw. Right. So obviously the shape is different. Now IF4 minus we just now saw. Right. IF4 minus belongs to AB4L2 category. So not AB4L2 category. Now this becomes square planar. IF4, I don't even want to speak about IF4. So what you understand is, depending on what charge is possessed by the molecule, say in this case, iodine has a positive charge. In this case, iodine is neutral. And negative charge goes to fluorine, right? In this case, it is positive charge on iodine. Here it is 0 charge on iodine. So you see the entire shape is changing. So definitely the shape will change if the ion or some neutral compound comes, right? Okay, so now like this questions can be asked. Now it becomes little more tricky if lone pairs comes into the picture. Okay, maybe we'll solve little more examples for you to get familiar with the shapes, right? So now let me take say SF6. SF6, let me take with XC. No. H2O, no. Why am I not getting? So I just trying to give you examples without lone pairs. And maybe let me, I don't want to make it complex. Let me just give PCl5. PCl5 will have, no, this is not a good example.
Sir, I have a doubt in this, sir. For example, PCl5, it has both 120 degrees as well as 90 degree, right?
Now those kind of questions will not be asked, don't worry. Okay, so when for this AB5 kind of complexes will not be asked in these kind of questions, because we know that there are 2 bond angles.
Sir,
Okay,
and
this
even
kind
for steric number 7, we have 120 and 90.
Steric number 7, we have 120 and 90. No, that would not be 120. For steric number 7, that is AB 7 type of molecules, it's pentagonal bipyramidal, right? So 360 divided by 5 is how much? 72, right? 72
Yes, yes,
degrees.
72 and 90. Sorry, 72 and 90.
72 and 90. Yes, correct. Right. But again,
So
these
which
kind
one
of
which
okay, right. So now all I want to remember is the shapes. But again, fine. Like we don't have to concentrate. I hope you understand. Right. So now if you know the shapes, if there are no lone pairs, it's very easy for us to do the problems because straight away you know the bond angles. Right. But if there is lone pair present, right? If there is lone pair present, then becomes a little complicated. Right. So now let us do that. Right. Say I have CH4, ammonia, and water. Okay, CH4, ammonia, and water. Okay, now this doesn't have any lone pair. This directly bond angle I can tell 109 degree 5 minutes because it's tetrahedral, right? No lone pair. Right. Now all of these molecules are actually having steric number 4, if you can remember. Right. This is AB4, this is AB3L, and this becomes AB2L2. Right? All of them are having steric number 4. Right? This we know for sure it is 109 degree 5 minutes. Right? Now NH3I, we already discussed this. The shape is going to be pyramidal. I have a lone pair. Nitrogen, nitrogen, nitrogen. Obviously, the bond angle here would be lesser than 109 degree 5 minutes because if this lone pair was not there and the bonding atom is there, obviously this bond and this bond would have been closer. Right? But since I have a lone pair here, the bond shift this side, thereby decreasing the bond angle. Right? Now, due to lone pair, bond pair repulsion. In H2O, what happens again? O, lone pair, hydrogen, hydrogen. First thing is I have a lone pair repulsion. Basically, they both will try to move away. And if they try to move away, obviously it will push my hydrogens very, very close to each other. Right? So now you can easily understand that CH4 will have the maximum bond angle, then comes NH3, and the least bond angle will be for hydrogen, sorry, H2O. Okay, right? So like these kind of questions can also come, right? These are very simple, right? These kind of things are very simple, right? Say now another example if I have to give you. I hope everybody understood this, why the order is like this. Any questions anybody has? Why the order is like this?
Sir, if bond angle increase, like if it increases in one side, the other side it would obviously decrease, right?
What do you mean by other side increases, this side it decreases? I don't understand.
Like for example, here in NH3, so due to extra repulsion, the angle decreases, correct?
Correct. This bond comes like this bond comes like this. Yes.
Yes, sir. But then the angle above is increasing, right?
You mean
between
this angle?
Yes, sir.
That angle we should not take, right? What is the angle? Bond angle means what? Bonding atom, single atom, bonding atom.
Yes,
that
sir.
bond,
Okay.
that angle you should take. This is a lone pair. You should not take that.
Okay, sir.
Understood? Right. Good. Right. So now I think everybody understood this. Why the order is like this, right? Say now, one last this thing, guys. Say I take everything possible. Okay, BF3. Say, but okay, SO42 minus. We already saw this, right? But still, SO42 minus. Say SF6 NO2 minus what else? NF3 H2S. Okay, so say all these compounds are there. Okay, can you arrange them in the order of bond angles? Okay, I'll take one more also. Wait, I will take okay, I'll take CO2. Okay, all of them are there, right? Can you arrange these species in the order of bond angles? So for all of them, you have
Sir, first one, is it BF4?
BF4, there's only BF3 here. take some time, right? So first what you do is for all of them, write the geometry and the shape for all of them, or at least the shapes. Geometry is not required. Try to write the shapes of all of them.
Sir,
Yeah.
sir, NO2 minus and NF3 both are going to be AB2L1.
NO2 minus will come under AB2L, right?
Yes, sir.
NF3 will come under AB3L. It's like NH3,
Sorry. Yes, sir. Okay, sir.
right?
Sir, shall I say?
Yeah, please go on.
Sir, maximum will be CO2,
Okay, first rank goes to CO2, then
BF3, 120 degree.
okay, then
Then NO2 minus, it would be lesser than 120 degree.
okay,
Then SO4 2 minus, that would be 109.5 minutes,
yes,
109 degree 5 minutes.
yeah, correct.
Then NF3, it would be lesser than 109 degree 5 minutes.
Okay, right,
Then
correct.
H2S, it would be very much lesser than 109 degree 5.
But greater
Yes,
than
sir.
90.
But greater
right?
than 90. And SF6 is purely 90.
Exactly. Yes, this is the correct order. Okay, I think everybody understood. This is linear, right? So obviously the bond angle is 180. Now this is trigonal planar. So obviously the bond angle is 120 degrees, right? Now then comes NO2. NO2 is of the type AB2L bent shaped, right? So obviously it will be little lesser than 120 only. Okay, little lesser than 120. So this goes to 3, and 3 goes to NO2 minus, right? Then comes NF3, which is having AB3L, which is literally lesser than 109 degree 5 minutes. Okay, right, which will be lesser than 1, and it is like NH3, right? And obviously just now we compared NH3 and H2O. It's like instead of O, I have sulfur, same group, right? So obviously that will be lesser than 109, but it will be greater than 90 degree for sure. Okay, it will be greater than 90 degree for sure, but because I know here it is 90 degree because it is octahedral complex, right? Octahedral will have 90 degrees, so that the last value goes to SF6. Okay, guys, this is how questions will be asked in your 1 mark also. Sometimes 1 mark also it can be asked. They can just ask you, give the molecules, and they'll give you 4 choices. Choose the correct order of bond angle. They'll ask. Okay, right? So these kind of questions will be fine. Now it's fine. Now we are able to get some grasp, right? Now, if I ask you these kind of questions, okay, see, look at this. For example, if I ask you H2O and H2S, or say NH3 and say NCl3, or say NH3 and PH3, or say PCl3 and PF3, right? If I ask you out, like say these are pairs, okay? If I ask you out of H2O and H2S, which will have more bond angle? Out of NH3 and NCl3, which of them will, which will have more bond angle? Same goes with this, right? Now, what you understand is all of them, basically these two are bent shaped. These two are pyramidal shaped. The shapes are exactly same, right? Again, this will be pyramidal. This would be again pyramidal. Anyways, right? So what you understand is all of them are actually pyramidal shapes. except for these two. These two are pent. Right? Now, same shape, same geometry, everything same, but just depending on the bonding atoms or say the central atom. Right? In this case, the central atom, bonding atom is changing. In these two, the central atom is changing. In this case, the bonding atom is changing. In this case, the central atom is changing. Right? So because of that, what consequence will I have? Okay, because of that, what consequence I am going to have is the question. Right? Definitely there's going to be some consequences. Okay, now I would say NCl3 will have NCl3 will have more bond angle, or NH3 will have more bond angle. NH3 will be towards that, and NCl3 would be, no, NH3 should have more bond. Or let us, oh, fine, anyways, we'll compare whatever it is. We'll try to find this out. Okay, right. Now first, like, how do we do this? Let me tell you. Right. Say for example, let me take NH3 and NF3. Okay, we'll come back to NCl3 later. Okay, so let us try to compare NH3 and NF3. We'll try to understand what is happening here. Okay, right. Now please understand, people, if I draw NH3 and NF3, same shape, there is nothing different. Right? Now what you understand is, for example, NH3, what I understand is there are bond pairs here. Okay, now obviously you're talking about each of these bond angles. Okay, now what I understand is nitrogen is highly electronegative compared to hydrogen. Right? Nitrogen is more electronegative. Correct? So now we know what you mean by electronegativity. Pulling the electron towards themselves. Shared pair of electron pulling towards themselves. That is what we mean by electronegative atoms. Right? So what I understand is if it is going to be exact in between, there is no problem. But what I understand is this bond pair will be more towards nitrogen. See, I'm not writing in between, or if I write it properly, wait. Right? Now the bond, say if it is in between, no problem, but you will see that the bond pairs are shifted more towards nitrogen because nitrogen is more electronegative. It will not be at the center. Okay, this bond pair will not be at the center of this nitrogen and this hydrogen, this nitrogen, this hydrogen. No. If I have same electronegativity, yes, they will be same. Right? But what I understand here is that here I have the bond pair shifting more towards nitrogen. Right? Now, if that happens, can you see that, say, let me compare it to the case like this. If, assuming, if they were in between, in the exact center, right? Can I say the distance between the bond pairs are little higher, right? But once they little go closer towards nitrogen like this, what is happening? The distance between between the bond pairs are decreasing. They're coming closer. You can see here they're a little far away from each other, right? But here the bond pairs are coming closer. So what will happen? The repulsion will happen, right? The repulsion will happen. So this bond will try to move away. Same way, this bond will try to move away, thereby little increasing the bond angle. Okay, they're getting diverged because of the bond pair moving towards nitrogen. Right? Now let us compare what happens in NF3. Right? In NF3, you can tell that fluorine is more electronegative. Right? Fluorine is more electronegative and all, but like say the electronegative difference is not so much. Right? The electronegative difference is not so much. Right? So I almost can say that it is almost in between. Right? The bond pair is almost in between only. Okay, right? So it is almost in between only, right? So that means what? Here, because of the lone pair moving towards nitrogen, the bond angle increases. But here, there's nothing happening like that because they're almost the same electronegativity. That is nitrogen and fluorine. Even the fluorine is a little more electronegative, but we can approximately say that nitrogen and fluorine are almost equally electronegative. Right? So that the bond pair of electron are staying right at the center. Right? So there is no such thing happening like this here. So can I tell for sure that NH3 will have more bond angle than NF3? Can I tell this point, people? Yes,
sir.
no? Right? I hope everybody gets this. What happens here? Right? The bond pair moves towards, the distance decreases, bond angle increases. They'll try to move away because they want to reduce the repulsion. And there is no such thing happening in case of NF3. Right? Okay. Now let us take NF3 and NCl3. Okay, NF3 and NCl3 we'll try to understand what is happening here. Okay, now same thing, NF3 we already discussed, the lone pair will be exactly the center, right? Even for NCl3, the bond, not lone pair, bond pair, I'm sorry, right? The bond pair will be at the exact center. Even for NCl3, you will find that the bond pair will be almost at the center only, right? But what I can now be able to understand is that people, chlorine also has lone pair on them. Right? Chlorine also has lone pair on them. Obviously, fluorine also has lone pair. No doubt about it. 3 lone pairs, everything will have. Okay, right. Now, these lone pairs can also suffer repulsion, right? Right? The lone pairs here, between this chlorine lone pair and between this chlorine lone pair, I can suffer repulsion. Right? Now, same thing can happen with fluorine also. But think about it and tell me. Think about it and tell me, where will these repulsion be more? I'm talking about the repulsion between the lone pair of fluorine and the lone pair of chlorine. Where it will be higher? Chlorine or fluorine? Where it will be higher? Think about it and tell me. Did you understand the question, people?
Sir, fluorine.
Okay, let us take a vote. Right? How many of you say fluorine? Go to the chat box, people. Go to the chat box and put, how many of you say fluorine lone pair repulsion will be higher, or say some if you find chlorine lone pair repulsion will be higher, put chlorine, right? Put F or Cl. Go to the chat box. Okay, Suprajit says F, Raghav says chlorine. Okay, others, come on, everybody participate. Chlorine spelling is wrong, Raghav. Yes, everybody participate. Ashwath, Hamsini, Kanish, Raghav said, Tarush, Sri Giridhar. Come on, everybody participate. Sri Giridhar says chlorine. Okay. Yes,
Sir, it
yes,
would be
yes.
Chlorine, sir, for sure.
We'll come to that. Wait. Okay, Hamsini says Cl. Okay, I think everybody answered. Yes, anybody wants to support their statements? Why fluorine? Suprajit said fluorine. Why fluorine, Suprajit?
Sir, no, sir. Actually, it's chlorine only. Now I realized.
Okay, I think Raghav changed his statement to fluorine. Why fluorine, Raghav?
Sir, I told chlorine only, sir.
You write chlorine only?
Yes, sir.
Okay, fine. So yeah, okay, fine.
I can say, sir.
Okay, how many? I think only who wrote? Only Suprajit wrote fluorine. Okay, fine. So all of you are saying that it is going to be chlorine. Why chlorine? Any idea?
Sir, in chlorine, their valence electrons are present in 3p orbitals, whereas in chlorine, it is present in 2p. So the repulsion in the electrons present in the 3p would suffer more repulsion than the electrons present in 2p orbital.
Why?
Sir, because they are far away from the nucleus and like close to each other.
That's the point, right? It's all about the atomic sizes here. Atomic size, obviously, the second point will come is the electronegativity. Is it not? Say if I talk in terms of atomic size, right? Fluorine atom is very small, right? Say fluorine atom is very small, lone pair. Another fluorine atom having lone pair, they will not have much effect, right? But if you look at chlorine, very big. So now the lone pair will be a little closer by, because chlorine atom is a little bigger, right? So now since they're a little closer, or I would say the atomic orbitals of chlorine are a little more diffused than in the case of fluorine. right? So obviously the chlorine lone pairs are more, as we said, far away from the nucleus, and this chlorine lone pair is also far away from the nucleus, so they will have higher repulsion. That is in terms of atomic size. Now, in terms of electronegativity also I can speak. Fluorine is highly electronegative, so it will hold on to its electron more strongly, right? Fluorine will hold on to its electron more strongly, so thereby it will increase the distance between the lone pairs. But chlorine is little less electronegative. It will not be able to hold on to its electron that firmly as in the case of fluorine, so the lone pairs become more interactive, so the repulsion is more. Right. So now, if the repulsion between the lone pair is more in chlorine, can I tell that again the bond will try to move away from each other? Right, because I want to avoid this repulsion now. So now NCl3, can I say that it will have a higher bond angle than NF3?
Yes, sir.
Yes. Right. Okay. Good. Now this we understood. Right. Now what about NF3 and NCl3? Now that's where the question comes. Both NH3 and NCl3 is having higher bond angle than NF3. What about NH3 and NCl3 is the question. Okay, guys. Now remember this. NCl3 will have more bond angle than NH3, and or I just want to confirm. Can someone Google it, please? Google
NCl3 only.
NCl3 is having the highest bond angle.
Yes, sir. Yes, sir.
Okay, fine. I remember it like this only. Right. Anyways, now this would be the bond angle order. Right. Now, why between NH3 and NCl3 I'm talking about this here? Because I'm talking about bond pair repulsion. Okay. But here in NCl3, we are talking about lone pair repulsion, but not in the central atom, but in the bonding atoms, obviously. Right. So here it is bond pair. Here it is lone pair. So obviously repulsion is more, but repulsion between, see, remember, repulsion, I'm talking about lone pair repulsion. Lone pair repulsion on central atom decreases the bond angle. You must have seen in the case of H2O. Oxygen is having two lone pairs, and compared to NH3, I have only one lone pair. Right. So I have a lone pair repulsion on H2O that decreases the bond angle. Right. But remember, when I have lone pair repulsion on the bonding atoms, that will increase the bond angle. The example I can tell you is NCl3, perfect example. Right. So don't get confused. You have to ask me, when I say lone pair, you must ask me, sir, are you talking about a central atom or are you talking about bonding atoms? You must ask me that question always. Okay. So in this case, I'm talking about bonding atoms, that is chlorine's lone pairs.
Sir, it's obvious, right? Because central atom is same in all.
Yeah, obviously. No, I'm just telling. Like, generally, when I say lone pair, right? A lone pair, which till now we spoke only about central atoms. That's why I wanted to mention this point. Okay, right. Good. So now we understood NCl3, NH3, and NF3. Right. Now let us move on. Let us move on to compare, say, NH3 with PH3.
NH3
okay, now
would
nitrogen and phosphorus belong to the same family, right? So basically, this will have one lone pair. This will also have one lone pair. Okay, right. Now, what can I tell about this? Right. Well, let us draw the. Okay, fine. Maybe we'll make it a little more interesting. Come on, guys, vote for me. NH3 or PH3, which will have higher bond angle? Vote it in the chat box. I'm looking at the chat box. Okay, Raghav says NH3. Come on, everybody participate. NH3 or PH3? It doesn't matter whether it is going to be correct or not, just a guess. Okay, Hamsini also said it's NH3. Okay, fine. Others? It's okay. It really doesn't matter. It's all about participating. Doesn't matter, Giridhar. Just give an answer. Doesn't matter. What do you think? Your answer is correct or not really doesn't matter. Whether you participate or not, yes, that matters a lot. Okay, fine. I think, okay, fine. All answers, like a majority of the answers were NH3. Okay, we'll try to understand this. Okay, right. Now, people, we have to look into lone pair, bond pair repulsion. Is it not? Both of them will have lone pair, bond pair repulsion. Correct. Right. Now, what you understand is ammonia is like this, and this is called phosphine. Okay, this is the common name. Okay, PH3 is what is called as phosphine, PH3. And this is ammonia. Okay, anyways, so in phosphine, again, the same shape, same everything, same geometry, same, but lone pair is there. Okay, now what? Okay, let me draw a little clarity, little more clarity. Okay, now there is a reason why I drew it bigger. Why did I do it bigger, people? Any idea? This I wrote little small, the lone pair, but here this lone pair is taking a lot of space. Why?
Sir, because it's present in the third period.
Exactly, because the atomic size is higher. Very simple. Atomic size of P is greater than that of N, right? So obviously the orbiter also bigger. Obviously, you can tell that this is going to be 2p, this is going to be in 3p, a bigger orbiter. So this takes up a lot of space. Okay, the lone pair of electron which is there in phosphorus is there in pp, or say the atomic size of P is very high than compared to nitrogen. So the lone pair on phosphorus will take up more space, right? If it takes up more space, can I say the repulsion between them will increase, right? The repulsion between this lone pair and this bond pair, the distance between them decreases because now it's become bigger, right? So obviously the distance between them will increase, right? So what will happen now? The bond pair will try to move away from the lone pair more than in this case. This also will try to move, right? But here it is somewhat little less. So comparing lone pair bond pair repulsion NH3 and comparing with that of PH3, PH3 has more lone pair bond pair repulsion, right? So if it has more repulsion, what happens now? The bond still goes further. So definitely NH3 will have a little higher bond angle than PH3. Okay, NH3 will have a higher bond angle than PH3 for sure. Okay, so like these kind of questions can come. Very, very simple questions, but like if you just understand the logic behind it, you don't have to mug up. The concept of by-hearting and mugging up is not anymore happening with our class. Definitely in chemistry sometimes, excuse me guys. Okay, fine, let it ring, it will be stopping anyways. I don't know to go there. Anyways, so what I was telling is, if you understand the logic, right, there is really there is no requirement that you have to mug up the answers. But in chemistry, yes, sometimes you have to remember things, but it's not like remember means, for example, something like say NH3 N2 plus H2 giving NH3, this reaction will happen only at 300 degrees Celsius. These kind of things you have to remember. There's no other way, right? But there are 95% of things in chemistry are logical. I don't know in what perception you have for chemistry, right? People think that I have to mug up a lot of reactions, I have to by heart this, by heart that. No, every reaction has some logic behind it. Every explanation in chemistry has a logic behind it, right? So please, like only when you try to move in that direction, then you will find more and more answers, more and more clarity, right? But if you sit in a shell and think that, okay, this is easier, I can just mug up and get marks, that's it. That eventually will happen throughout your life, not here in college, say MSc, PhD. If you just continue, this will keep on happening. Okay, anyways, so we understood now, right? Now let me give you some shortcuts, right? The shortcuts for bond angle. Okay, now first, electronegativity of central atom. That's the first criteria. Like in this case, you see the nitrogen, where is it? Nitrogen and phosphorus are having different this thing, the electronegativity, right? And what is happening here? NH3 is having more bond angle, right? So I can tell electronegativity of central atom is directly proportional to the bond angle. This is the first category you can choose. Again, there's a logic behind this, right? We understood the logic behind this, right? Electronegativity of central atom is directly proportional to the bond angle. Second one, electronegativity of bonding atoms. Now that we saw in the case of NCl3 and NF3, what happened? NCl3 had more bond angle, right? So now in this case, electronegativity of bonding atoms, again, that is also directly proportional to the bond angle. Okay, now these two simple points, if you remember, done. Any kind of questions can be solved according to with respect to bond angle. Okay, electronegativity of central atom is directly proportional to the bond angle. Okay, the both BA, you write bond angle here if you don't want to get confused. Okay, this is bonding atom. Okay, so electronegativity of bonding atom is also directly proportional to the bond angle.
Sir?
Very, yes, tell me.
Isn't it inversely proportional for the second case?
NCl, oh yes, absolutely. I'm so sorry. Yes, because NF3 had lesser bond angle, right? Yes, correct. Thank you for reminding me. Right, so electronegativity of bonding atom is inversely because I know NCl3 in NF3 fluorine is more electronegative, but NCl3 has more bond angle. Yeah, it's absolutely true. Okay, right. So these two are the points you can remember, and any kind of questions can be solved. And obviously, this will come only if the say these kind of molecules. Say, this will work only for same shape molecules. Right, this particular shortcut which I gave you will only work if I have same shape. Like these two are having same shape. All the examples we got, like say last 10 minutes, all are having same shapes. Right? Okay, now if I ask you H2O, H2S, which will have a higher bond angle?
H2S.
Are you sure? It's going to be H2O, right? Look at the first point. Electronegativity of central atom more.
Central atom is S, right?
What?
Central atom is S, right?
Exactly. Central atom is S here, and central atom is oxygen here.
Electronegativity. Oh, yes, sir. Electronegativity of oxygen is greater
than that of sulfur. So definitely H2 will have more bond angle, or you can again go for the same thing explanation. Oxygen having 2 lone pairs. Sulfur is also having 2 lone pairs. Right? Now these lone pairs are very big, right? So they will move very far away from each other. I mean, so that this will constrict so much, but here it will be only a small movement because these lone pairs are little held strongly by oxygen. Right? Either you go by the shortcut or you go by the logic, you will get the same answer. Okay? Right? Fine. But remember, this will work. The shortcut which I told will work only on and only if I have same shape. If I don't have same shape, like this you have to do. Like we saw examples like this. Like say this, like this kind of questions. You have to know the shape, you have to know the geometry, and accordingly you have to decide which is going to have more bond angle, lesser bond angle, all that. If they have same shape, then you can look at this, whatever we wrote here. Okay. So these kind of questions, definitely one question or 2 questions will come. One question for sure it will come in your midterm exams or whatever exam which you're going to write. Okay, what is the time, guys? Let me see. Okay, you have 20 more minutes. Right, we'll continue. Right. So next thing what I want to speak, that's about the bond angle problem. Okay. So next thing what I want to speak about is ionic nature in covalent compounds. Okay, ionic nature in covalent compounds. Basically, if I have to, this entire thing, I can use just one word to describe this. I am going to speak about dipole moment. Okay, I am going to speak about something called as a dipole moment. Right. Now, first we'll try to understand how ionic nature exists in covalent compounds, and then we'll try to understand what is dipole moment. Right. Now, we already discussed this, people. Say I have HH covalent compound, HCl covalent compound, and say ClCl covalent compound. right? Now, what I understand is all I have to look into is where the bond pair is there, right? Now, you will understand that the bond pair will be at the exact center of these two hydrogens because they both have same electronegativity. Same goes with your chlorine, exactly at the center because they have same electronegativity, right? But if you check HCl molecule, it will be more towards chlorine and away from hydrogen because chlorine is more electronegative than hydrogen. Is it not? Now, because of this, what is going to happen is the question, right? Now, because of this, now if the electron pair is exactly at the center, no problem, they are neutral. In this case also, they both are neutral, right? But once the electron cloud is moving towards one of the atom, right? Say I am neutral, something negative comes towards me, obviously I will also attain the negativity, right? So what happens here is that since the electron cloud is moving towards chlorine, chlorine is going to attain a negative charge, but not a full negative charge. It's not like Cl minus. No, it is a partial negative charge. This del minus, I'll write a S kind of thing and I put a negative sign, right? Now this del, whenever I write, it is partial, right? So when I say del negative, partial negative charge is what I have on chlorine. Okay, but what you have to understand is overall the compound should be neutral, right? Overall the compound should be neutral. So what I understand is the electron cloud is moving towards chlorine, so negative charge on chlorine. Can I say electron cloud is moving away from hydrogen? That will induce a partial positive charge on iodine, hydrogen, right? Electron cloud moving towards chlorine, so partial negative charge on chlorine. Electron cloud moving away from hydrogen, so partial positive charge on hydrogen. Something I have negative, it moves away from me, so obviously I become positive, right? So hope you understand now. Now you see this separation of charges, right? These separation of charges, whenever it happens, these kind of molecules are what are called as polar molecules. We already told ionic compounds are polar. If you remember, when we discussed ionic compounds, we told them that ionic compounds are polar. Basically, polar means I will have some charge separation, right? Ionic compounds are perfectly polar, completely polar, right? But here, these are partially polar molecules. Why partially polar molecules? Because I have only partial charges here, not a full positive and full negative charge, right? But generally, we call them as polar molecules, generally. Okay. Right. So hope you understand why this kind of charge separation is happening. Again, you see there is a charge, negative charge, positive charge. This is why we say ionic nature exists in covalent compounds. Right. Now, not all covalent compounds are having ionic nature. Just now we saw H2 is an ionic covalent compound, Cl2 is a covalent compound, but no ionic nature. Right. Now, when can I have ionic nature in covalent compounds is only when there is difference in electronegativity between the bonding atoms, right? On and only if, right? On and only if there is difference in electronegativity, right? Not electronegativity, difference in electronegativity between the bonding atoms, then only I can tell that these are having some ionic nature, or I can call these molecules as polar molecules. Okay, I can call these molecules as polar molecules. Basically, it means they have some ionic nature. Okay, this point I hope is very clear, right? Say now, if I ask you this question, say just random thing, okay? BRF is a compound, just like Cl2 or Br2, instead of that Br, I have put one fluorine. Okay, now let me compare it with ClF. Okay, now can you tell me which is, okay, for first question, are both of these things polar?
Yes, sir, they are.
Yes, because definitely fluorine and bromine have different electronegativity. Chlorine and fluorine also has different electronegativity. Right. Now my question is, which is more polar?
The BR.
Right. Good. Now remember, guys, polarity, or say the ionic nature, is directly proportional to the difference in electronegativity. Right. Very huge difference in electronegativity, very huge charge separation. right? So what I'm trying to tell you is that, say the electronegativity value of, I'm just giving you random values. Okay, electronegativity value of Br is 10 and this is 20. Okay, now chlorine's value is 15 and fluorine is same 20. Right, now what is the difference here? Difference is 10 and here the difference is 5. Right, 20 minus 10 is 10, 15 minus 20 minus 15 is 5. Right, so definitely there is more difference in electronegativity in BRF. So if I tell, say this is, obviously it will be, the electron cloud will be more towards fluorine. In this case also it will be more towards fluorine because fluorine is more electronegative. Right, say this will be del 1 negative, this will be del 1 positive. Right, del 1 negative, del 1 positive, this would be del 2 positive, and this would be del 2 negative. Okay, so basically what I'm trying to make you understand is that there is charge separation happening here in both these cases because there is some electronegativity difference, right? But the amount of charge is developed, you see, on both fluorine, bromine, chlorine, fluorine, the del 1, del 2 values are different, and I can blindly say that del 2 is greater than del 1. Del 2 is greater than del 1 because there is more I'm sorry, I'm telling the opposite. Del 1 is greater than del 2 because del 1 is here, BRF. Okay, del 1 is greater than del 2 because why? There is more electronegativity difference here. Here there is less electronegativity difference. Do not only talk about electronegativity. It's always about difference in electronegativity. Okay, I hope you got the point now. Right. Okay, now keeping this in mind, right, we'll talk about what is this dipole moment. Okay, right, now we understood how ionic nature can exist in a covalent compound. Because there is difference in electronegativity, there can be separation of charges, partial positive, partial negative. Very simple. Right, now let us try to understand what do you mean by dipole moment. Right, first thing, what is a dipole? First we'll try to understand. Okay, what do you mean by a dipole? I think from the name itself we can understand two poles, positive pole, negative pole. Okay, so a dipole, a physical explanation, a scientific explanation, if I have to give you for a dipole is an arrangement of two equal and opposite charges. Right, it's an arrangement of two equal amount of charge, say +2, -2. Right, equal charge, but equal magnitude, but opposite charges. Right, so it's an arrangement of two equal and opposite charges separated by a distance. This is the exact definition I can give for a dipole. You will study again about this in 12th class, but not in chemistry, but in physics. Okay, in your chapter 12th, first chapter, electrostatics. Okay, in that chapter name, first chapter in 12th, right? You will get very good insight into this dipole moment, dipole, what are these, everything. You will get a very good picture. But for chemistry purpose, we will just touch it. That's it. Okay, right, fine. So as I told, dipole is an arrangement where there are two equal and opposite charges separated by a distance. So if I have to draw it properly, people, I have one charge which is +q, and there is another charge equal and opposite, and they are separated by a distance d. This arrangement is what is called as a dipole. Okay, dipole is an arrangement, right? Now, dipole moment is a quantity. Like how you have distance, displacement, velocity, acceleration, like that, dipole moment is a physical quantity. Right, dipole moment is a physical quantity. Okay, now what I have to understand is, I know physical quantity can be of two types, scalars and vectors. Right, now what I have to understand is, dipole moment is a vector quantity. Dipole moment is a vector quantity, means it has both magnitude as well as direction. Okay, magnitude as well as direction. Okay, and it is denoted by the letter mu. That is, you put a line and you draw u. That is what is, this is mu. Okay, the symbol for dipole moment. Okay, So dipole, first you have to understand what is a dipole. Dipole is two equal and opposite charges separated by a distance. What is dipole moment? I'll tell you what is dipole moment. Don't worry. For now, dipole moment is a physical quantity, which is a vector quantity, and it is denoted by the letter mu, Greek letter mu. Okay, right. Now, what is the formula for dipole moment? Mu is equal to Q into D. Very, 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 very simple. Okay, mu is equal to charge into the distance, basically the amount of charge I have here, whatever be the charge, -2 coulombs, 3 coulombs, whatever it is, right? Now, only the magnitude, plus or minus doesn't matter, only the charge value, right? Into the distance between them, right? Now, please understand, if for example, if I take HCl, right? Now, I'm just telling you, how do we visualize this in your chemistry? Like, how do you visualize dipole moment in chemistry? We already know there is a del negative, del positive, or chlorine and hydrogen respectively. Now, are there not equal and opposite charges? Right? Del positive, del and del, plus and minus, same charge but opposite signs, right? And obviously it is separated by a distance, and the distance is what here? What is the distance? Now, I'm not asking about the value. What can you comment about the distance here?
Sir,
Again,
it's less.
No. I mean, okay, maybe I'm not able to put the question the right way. I'm telling that the distance that I'm talking about here is nothing but the bond length. Hope you understand, right? So basically, there should be some equal and opposite charges separated by a distance. Now, here I have del negative and del positive, and the distance between them is nothing but the bond length of this particular molecule. What is bond length? Between this nucleus and this nucleus, there'll be some distance. That is what is called as the bond length. And that's exactly what I need, right? This is an exact arrangement for a dipole. Is it not? Right? So there are two equal and opposite charges separated by a distance. In chemistry, that distance is nothing but the bond length. Not only for this molecule, any molecule for that matter. Okay, if I have a polar molecule, for sure, I know I'm going to have separation of charges, that is del minus and del positive will be there, right? And what is the distance for the dipole moment here? In any compound where you have a separation of charges, the distance for the dipole moment is nothing but the bond length. Okay, right. Now, next thing is, okay, this is the magnitude, right? Or I told you this is a vector, right? Mu is a vector. We put the symbol, arrow mark symbol at the top, right? This is a vector. Okay, magnitude is this. Q into D. Okay, before this, what is the unit for this thing? You can see, right? This is coulomb, and this should be meters, right? For SI unit of charge is coulomb, for distance it is meter. So for this thing, it is going to be coulomb meter. Okay, coulomb meter is also called as, is it diopter? Diopter is for power. Coulomb meter is also called as what? Oh God, I forgot. Coulomb meter is also called as. Okay, guys, don't worry about this. This I'll tell you next class. Okay, now you can understand how is a coulomb meter, right? Coulomb for charge, meter for distance, right? So the unit of dipole moment is coulomb meter. Now this is the magnitude, right? What is the direction, right? Remember the direction in chemistry. We are talking only with respect to chemistry. Okay, right. Now the direction, there are two possibilities, right? Now, when no lone pair is there, okay, we'll come back to this point. Okay, when there is no lone pair, the direction is towards more electronegative atom. Okay, for example, in this case, I don't have any lone pairs, right? Okay, I don't have any lone pairs. Obviously, chlorine has a lone pair, but still, I can tell that the dipole moment direction is in this direction, right? Towards the more electronegative element. Let's say, for example, if I have BRF, it will be towards F. Okay, so when there is no lone pair, it is going to be towards the more electronegative element. Okay, now when I have lone pair, when the lone pair is present, right, the direction is towards the lone pair. Okay, now if at all I have to give you a proper example, like say NH3 molecule, let me take. Okay, now NH3 molecule has a lone pair also. Now look at this. This bond is polar. So now this, see, you have to talk about dipole moment for individual bonds and then do the vector sum if I have so many bonds. In this case, I have only one bond, so there is no problem. Only one dipole moment, directly only one is there. This is the resultant also. We know, right? There's something called as resultant vector. Right now, what you understand is in NH3, there are 3 bonds like this. So they three of them will have not different lone pairs, but the 3 bonds there will have 3 dipole moments, right? And where should they point along? Can I say in this case for this 3 bonds, right? It is going to point towards nitrogen, towards nitrogen, towards nitrogen. Okay. Right. And whenever you have a lone pair, people, it should point towards the lone pair. Right. So totally in this case, there are 4 things. Say this is mu1, this is mu2, mu3, and mu4. These many dipole moments I have. Right. And obviously, how will you get the mu bar? That is your resultant vector. If I call them as resultant vector, you must go for parallelogram law of addition. Right, like we can. I think we don't have time for discuss today. Right, hope you understand what I'm trying to say. If there is lone pair, right, the dipole moment will be towards the lone pair. If there is no lone pair in this particular case, there's no lone pair here, and that is going to be towards the more electronegative atom. More electronegative atom in this case is nitrogen. Okay. Right, we will speak about this in detail. Okay, don't worry, we'll take a lot of examples. Now you understood what is dipole moment, and how are we going to incorporate this in chemistry. Okay, now we'll take more examples to understand how are we going to do the rectangular parallelogram addition, how do we take the resultant. All these things we'll try to understand in the upcoming classes. Sir? Okay, yeah, tell me.
Sir, is the unit of Coulomb meter dBy?
Yeah, thank you so much. Okay, Coulomb, DEBE. That's the unit. Coulomb meter is nothing but this is like dBy was a scientist who talked about dipole moment, so that's why the name was given to him. dBy is nothing but Coulomb meter. That's the unit of dipole moment. Yes, thank you. Right. Okay. Any questions anybody has, people? Today we saw about steric number 6, 7. We saw about bond angle problems, and I just introduced you. Not even introduced you. Almost everything is over in dipole moment. We just have to see some examples and try to understand how this works. Right. After that, we have to go for molecular orbital theory. Okay. I thought I'll complete molecular orbital theory today, but I don't think it's definitely it's not possible. Right. So guys, will you manage molecular orbital theory? Don't worry, I will teach you, but for your exams, I'm asking. Right. If before I teach, if your exams comes, will you be able to manage molecular orbital theory alone?
Sir, can you tell like how will the questions be asked from that?
How questions will be asked from that?
Yes, sir.
See, are you having only MCQs?
Yes, sir, only MCQs.
Yes.
And assertion and reasoning also.
Blindly go for it. Just remember the bond order formula. Bond order formula is now half into number of atoms in bonding orbital minus the number of electrons in anti-bonding orbital. This formula you remember. Okay, now this bond order is directly proportional to stability.
Yes.
Right, that is one thing. More bond order, more stability. Okay, and it is inversely or directly proportional to bond strength also. Obviously, that is also understood. Right, and it is inversely proportional to the bond length. This also we saw how bond length and bond strength are related. We already saw this. Right, fine. This is one thing. Right, now if bond order is same for 2 species. Right, if bond order is same for 2 species, like for example, let me take Li2 1 plus and Li2 minus 1 minus. Okay, now if I ask you to arrange them in the order of stability, right? Now let me understand. Li2 has 6 electrons, right? 3 electrons for 1 lithium, 6 electrons. So I'll write sigma 1s2, sigma star 1s2, sigma 2s2. This is for Li2. For Li2 plus, we write sigma 1s2, sigma star 1s1. Right? Oh, sorry, sigma star 1s2 and sigma 2s1, because now 6 electron becomes 5 electron because I have plus. Right? Same way for Li2 minus, it would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s1. Right? Okay. Right. Now to calculate the bond order in both of these, in all the cases, bond order in this case will be half into number of electrons in bonding orbital is 4, anti-bonding is 2. So will it be 1? The bond order is 1. For Li2 minus, you calculate bond
0.5.
order. Yeah, 0.5 you can easily do. Say 3 electrons minus 2 electrons will become 0.5. Right. If for Li2 minus also you calculate, it will be 0.5.
Yes, sir. 0.5. Yes, sir.
Okay.
0.5.
Now I told you more bond order, more stability, right? And more bonds and everything is there, right? But if I have same bond order, and if they ask you for stability, now the one which has electrons, or say more electrons in anti-bonding orbitals, ABO, right? In anti-bonding orbital is less stable. Or I can even tell the one which has more electrons in bonding orbital is more stable. Hope you understand, right? So if I have more number of electrons in anti-bonding, it becomes less stable. If I have more electrons in bonding, it becomes more stable. Hope you understand what I'm trying to say. Now look at this. I have Li2 plus and Li2 minus both having 0.5 and 0.5. Okay, now look at this. I have only 2 electrons in anti-bonding in case of Li2 plus. But look at this. I have 2 electrons here and 1 electron here. 3 anti-bonding orbital electrons. Here I have only 2 anti-bonding orbital electrons. Okay, now I can blindly tell that this is the order of stability. Right?
But
Why?
the number of bonding electrons is same in both, sir.
Yes, correct. Either you use this term or this term, whichever works. For this question, this works. That is, the number of anti-bonding electron is different, so I'm taking that. Whichever
So
works
we
for
have
the
to check both.
Sorry?
We have to check both. For example, if the number of bonding electrons is same in both, we have to go for anti-bonding electrons.
Correct. Yes. Okay, so in this case, you see there are 2 electrons only. Here are 3 electrons in anti-bonding. So Li2 plus will be more stable. Okay, another thing what you have to understand is about paramagnetism and diamagnetism. Right now, actually, I can talk about this in a very little detail, but for just a shortcut, if unpaired electron present, then it is paramagnetic. No, all paired electrons, it becomes diamagnetic. Okay, now this is how questions will be asked. Okay, so they might ask you to find the bond order. They might ask you to arrange them in order of stability or bond strength or bond length. It depends on the bond order. Or lastly, they can tell which of the following species are paramagnetic or diamagnetic. These kind of questions only will come. Okay, right? Now we will spend some time on all of this. What do you mean by sigma 1s, sigma star 1s? How is an anti-bonding orbital formed? How a bonding orbital? The mathematics behind it a little bit, right? And what do you mean by this paramagnetism, diamagnetism? How exactly will I be able to give an explanation, physical explanation? All these things we'll see in detail. But for you to write your exams, this is sufficient. Okay, bond order calculations with respect to bond order, all the other things, how it changes, and about the magnetic properties. This alone is what is required. Okay, guys, fine. You must be able to survive, not even survive, get full marks. Molecular orbital theory understanding is a little difficult, but doing problem is very, very easy. Very, very easy. Okay, now you will be able to score full out of full in your molecular orbital things. Okay, so now bond dipole moments, you don't have to worry about it. Okay, don't worry about it. Right, one question will come. You can manage, not a big deal. Right, don't worry about it. Right, any questions anybody has?
Sir, for example, not asking from my exam point of view, but for example, if we take H2O molecule and we calculate the dipole moment, and when we do the vector sum, it is not coming. We can tell that it is non-zero.
Yeah, it is non-zero.
Yeah, but how do we find what's the exact value?
No, that will not be able to do, because you can do in the sense Q value, you can do it. Basically, okay, if I talk about the distance, right? First of all, you need to know the distance, right? For that, you need the bond length values that you can get, right? And this Q can be calculated. Q again can be measured with the help of some instruments. Very sophisticated instruments are there, right? You can measure it. But for your level, there is no calculation. What kind of question they'll ask is, say, comparing to H2O and NH3, which has more dipole moment? Obviously, I can tell that H2O has more dipole moment because it has 2 lone pairs.
Yes, sir.
Right? So like that, questions can come. They will not ask you to find the dipole moment of H2O. They might ask questions like this. They will give you the Q value. They will give you the D value. Then ask you to find the dipole moment. This can be asked. But they will not just give the molecule and ask you to find the dipole moment. No, that is not possible.
Okay.
Okay. Right. Any other questions anybody has regarding your exams?
Energy level diagrams will be asked.
Energy diagram, ideally we should know, but since it is going to be MCQs, they cannot ask you energy level diagram. So don't worry about it.
Same goes
Okay.
to a hybridization diagram.
Yes. Same goes to hybridization diagram also. Yes, correct.
Okay, so then redox reaction balancing, how will
Redox reaction balancing. Use oxidation number method, right? What to do? Fine. Let me take 5 minutes. Maybe I'll just give you one example. Okay, right. Say I have MnO4 minus reacting with Fe2 plus forms Fe3 plus Mn2 plus. And this is happening. What medium it is happening is very important, guys. It's happening in acidic medium, assuming. Okay, right. Now, how will you balance these kind of things is very easy. Okay, now what I will follow is what is my half reaction method. I don't want to follow oxidation number method because that might become a little complex. Okay, so when I go to half reaction method, right now what you do is check for the species. Obviously, MnO4 and Mn is one pair, and Fe2 plus and Fe3 plus are one pair, right? So, like, okay, we'll try to understand. Or just check which element is getting oxidized and which element is getting reduced. That you can tell easily, right? Because MnO4, if you calculate the oxidation number will be +7. And here for manganese in the product side, it becomes +2. Right. So we know that whenever I have reduction in oxidation number, decrease in oxidation number, that is going to be reduction. Okay. Now, what you do is first you write for MnO4 and MnO2. MnO4 becomes Mn2 plus. MnO4 minus becomes Mn2 plus. Right. Now, for +7 to become +2, what should have happened? Obviously, I should have added 5 electrons to MnO4 minus. Okay, obviously I should have added 5 electrons to MnO4 minus. This is one reaction for MnO4 and Mn2 plus. Next reaction is Fe2 plus is becoming Fe3 plus. Right? Now what should have happened? Obviously, for Fe2 plus to become Fe3 plus, Fe2 plus should have lost 1 electron. Okay, Fe3 plus should have lost 1 electron. Okay, now what are you going to do? This is your oxidation. Okay, this is your reduction. And this is your oxidation. Is it not? Right. Now, what is the next step? This is the first step, basically, right? Check. Okay, the first step is to check which element is undergoing oxidation, which element is undergoing reduction. That is the first step. Second step is to write the half reactions. Write the reduction reaction separately, write the oxidation reaction separately. Second step. Third step is make the number of electrons lost and gained to be equal. Say, I'll write first step is identify oxidation and reduction. Second point, write the half reactions. That is your oxidation half reaction and the reduction half reaction. Third, right? Third, make number of electrons gained equal to number of electrons lost somehow. Now, how will you do it? For example, in this king, I have 5 electrons gained and 1 electron lost. So I can easily multiply this overall reaction by 5. Okay. Now, if that happens and you write it, so what happens now? It becomes 2 Fe2 plus becomes 2 Fe3 plus 5 electrons, right? Then fourth step is add half reactions, right? Now, basically after making it equal, right? So basically you have to take 1 and say this is 2 after
How is
multiplying,
it
right?
2 SP? It should be 5,
Sorry?
right?
Oh, I'm so sorry. I'm so sorry. It's 5. Five and 5. Yes, absolutely correct. Right. Now you add these two. So what will happen? MnO4 minus plus 5 Fe2 plus 5 electron gets cancelled. Okay, 5 Fe2 plus gives Mn2 plus 5 Fe3 plus. Okay, now done. You got this. Last step is charge balance. Right now, charge balance depends on the medium. Right, if it is acidic medium, you have to add H plus. If it is basic medium, you have to add OH minus. And accordingly, you have to now as many H plus you had, you have to make sure that it is getting balanced with the help of water molecule. Anyways, now let us see what happens here. Right now, what do you mean by charge balance? Calculate the total charge on the reactant side and calculate the total charge on the product side. Right now, you see here I have -1 for MnO4 minus, and there is 2 plus, but there are 5 such 2 pluses. So can I write it as plus 10? 5 into plus 2, right? Totally what I have is -9 on the reactant side. Now go to the product side. Here I have plus 2 for manganese, and here I have 3 plus for iron, but I have 5 3 plus, so it becomes 15. So 2 plus 15 will become 17. Okay, so here I have -9, here I have 17, right? I have to make sure that somehow it's equal. Now, for me to make it equal, I have to look into what condition they have given. They have given it to be acidic condition. So you have to add only H plus. Okay, right. Now, I have to make sure that something I add here, some positive thing I add here, so that becomes equal to 17. What should I add here? What is the number should I add here?
25. 26.
26. Right, so what I have to do is add 26 H plus here, right? Add 26 H plus in the reactant side, so that now if you calculate plus 26 will become equal to 17. Right now, you cannot just finish it here. Last step after charge balance, balance hydrogen and oxygen by adding water. Right now, you don't worry about oxygen in this case, worry about hydrogen. So you have 26 hydrogens. So in the product side, I can put 13 H2O. Don't worry about oxygen here, right? You need to have 26 hydrogens, 13 into 26, 26. Yeah.
Sir, -1 plus 10 is +9, right?
Oh, I am so sorry. Yes. Right. So +9 means
so 8.
This value should be 8, right? Absolutely correct. Right. So this should be being 8. So now it's not 26 H plus, it is 8 H plus. Right. And this should be 4 H2. Okay. Anyways, the overall thing is you have to understand. Right now, just follow these steps. Identify the oxidation reaction, reduction, what is happening. Write the half reactions. Then you make sure the number of electrons gained and lost are equal by suitably multiplying. Then add the half reactions. Then at last you have to go for charge balance, looking at whether it's acidic or basic medium. And after doing that, balance for hydrogen or oxygen by adding H2O on the appropriate side. Okay, right. Now you have to be very careful with this. See, I'll just give you, there can be issues like this. Okay, say Cr2O72 minus, same example I take, Fe2 plus becomes Cr plus 3, and this becomes Fe3 plus, say acidic medium. Again, I'll quickly do this. I'll just take 2 minutes. Okay, now I know chromium will be in +6 and this is going to be in +3. Okay, right. Now the first thing, whenever you have a difference in number here, you see there are 2 chromium atoms, but there are only 1 chromium atom here. You have to be very careful in these cases. Okay, now write the half reaction. Cr2O72 minus becomes Cr plus 3, right? So obviously for this to happen, I should have chromium Cr2O7 should have accepted 3 electrons, right? Okay, now but understand, for one CR6 plus, to become CR3 plus, 3 electrons are required. But how many CR6 pluses are there? 2 CR6 pluses are there. Sorry, 6 plus are there because CR2, right? The moment you see a difference like this, match it, put 2 here. Okay, now the moment you match it, then you can see for one CR plus 6, 2 becomes CR plus 3. You need 3 electrons. But in this case, since 2 CR6 plus becoming 2 CR3 plus, I require 6 electrons here, not 3 electrons. If you put 3 electrons, done. The entire problem is wrong. Okay, obviously the other one is very simple. Fe2 plus will form Fe3 plus by removing an electron, by losing an electron. So this will be multiplied by 6 and you add it. So you have Cr2O72 minus plus 6 Fe2 plus becomes 2 Cr3 plus 6 Fe3 plus. Right now, if you go for charge balance,
Sir,
yeah, tell me.
sir, the charge of Cr in Cr2O 2 minus is +6, right?
Yeah, plus 6, yes. Right, it is plus 6 and it is becoming plus 3. Okay, right. So now look at the charge balance here. -2 plus 12, 6 into plus 2. This is basically 10 in this case. And say in this case, it is plus 6 plus 18 will become 24, plus 24. So I have to add, can I say, it's an acidic medium. So can I say I have to add 14 more, so it becomes 24. So basically I have to add 14 H plus, and obviously I have to add 7 H2O on the product side. Okay, this is the entire balanced equation for this. Right now, why I mentioned, one second, why I mentioned this is because you have difference in number here itself, Cr2 and Cr. So you have directly put Cr. That's the first step here. Okay, yes, please go on. What is the doubt?
Sir, can you show the previous example, the first one which you did?
Yeah.
Oh, okay, no, sir, never mind, sir. I got it.
Understood? Yes. Okay, right. So whoever asked for it, is it fine, Kana? Now you'll be able to manage the redox reactions balancing. Is it fine now?
Yes, sir.
Okay, right. Cool. So we took a lot of time, right? But it's fine. It's worth it, right? Any other questions anybody has regarding your exams?
Sir, can you explain that doubt which I had asked in WhatsApp? Like,
What do you ask?
why in the transition series, sir?
Oh, I replied you, right? I replied you. Basically, the transition series you asked me, basically 3D is having more energy than 4S, right?
Yes,
Why
sir.
is it that they're filling 3D? Sorry.
Yes, sir. Correct only.
No. This is 4 and this is correct. Okay. Now this is very simple. I have to fill the electron in 4S, then only go to 3D. Even though we write 3D5 4S2 something like
Yes,
that,
sir.
but it's actually 4S2 3D5. This is how
Yes,
we
sir.
write
This
it.
is what I was asking. Like,
Yeah,
it should be
This
4S
is
to 3D.
exactly before 3D 4S has to be filled. Yes, that's it. That's the point.
And why do we write like that, sir?
This is just because I know like the third shell is behind the fourth shell. That's why we write like this. But properly writing, this is how we properly write. This is not a correct way of writing. This is the correct way of writing.
Sir, and how to find the valence electronic configuration? Like here, is it only 4S2 or even 3D should be included as a valence electron?
For transition metals, right, you have to take NS, how many other electrons you have, and N-1 d orbitals, how many electrons you have. Both say this is X, this is Y. The valence electrons would be X plus Y. This is our mistake.
In case we had to add one electron, in which orbital should we add? D or S?
Okay, that's a very good question. If you want to add an electron, we'll add it to the valence shell. That will be 4S.
Then we should write only 4S, right? Why D?
No. But that happens because if you look at the bond formations in your transition metal series, right, you will understand that more than S orbital, it's the D orbital which is involving in the bonding. That's why we take this D into the picture, or else we'll not take. Okay, you will get more insight when you go to 12th class. There is a separate chapter called as D and F block elements. Okay, there you'll get more clarity. So all you have to understand now, why am I including this D here, is that it's because the D orbital is involving in bonding somehow. Even their hybridization will come, so many things will come, right? That time you will see. But for now, D orbital involves in bonding very, like say, more than 4s. That's what you have to understand.
Okay, sir.
Right. Any other questions anybody has? Okay, fine.
No, sir,
Let me stop
that's
here. Okay. Cool then, people. Thank you so much. We'll meet again next week. Right. I'll end the class.
Thank
you,
you, sir.
Thank you, sir.
Thank you.